Hey everyone, welcome to July ASES webinar. I'm going to give everyone just a couple minutes to join in here before we get started, but welcome to ASES's July webinar. Okay, well, welcome everyone. Let me here.
Okay,
So
I'm ready.
We've got Roland Winston here today. I'm Carly Cipolla. I'm the Director of Operations for the American Solar Energy Society, and I'd like to thank everyone for joining us today, where we'll be talking about solar energy from a 21st century perspective. Before we introduce today's presenter, I'd like to give you all a short update of what's going on for ASES programs. Our 49th Annual National Solar Conference, Solar 2020 Renewable Energy Vision, took place live last month, June 24th and 25th, but is still available to register online for you all to check out the virtual lobby, exhibit hall, and networking lounge. We also have the auditorium still available to go into and watch all of the recorded content and sessions from the conference. I'd like to thank everyone on the webinar today for joining us by giving anyone who hasn't registered yet for the conference a 10% discount with promo code THANKYOU2020. Please register before July 25th, as access to the virtual conference will no longer be available after that date, but you will still have access if you register before then to all of the recorded content. So please do still register if you're interested in watching any of the sessions from the conference at solar2020.ases.org. This is also a really big year for the National Solar Tour. It's our 25th anniversary of our nationwide grassroots event, and it is also going virtual this year with a whole extra week of online events. It'll be September 28th to October 4th, where ASES and Sun are offering daily virtual events and tours of solar homes, businesses, schools, and more. You can learn more and sign up to host an open house or a local tour at nationalsolartour.org. You can also learn more about upcoming events from ASES and our partner organizations at ases.org/ASES events. I'd also like to remind everyone that our webinars will continue to be free during this unprecedented time. And you can learn more about the ASES webinar series, including what's coming up next, at ases.org/webinars. Our August webinar will be on August 6th at noon Mountain Time, and will be all about the National Solar Tour. So be sure to register online for that on ases.org/webinars. Now I will hand the mic over to Dr. Roland Winston, or Casey if you are online, to introduce Roland, and we will get started with today's webinar. Thank you all.
Thank you, Carly. This is Casey. I can introduce Roland real quick. So Dr. Roland Winston is a distinguished professor and founding faculty member in the Schools of Natural Science and Engineering at the University of California at Merced, also known as UC-Merced. And he is also the director of its Advanced Solar Technologies Institute, or UC Solar. Dr. Winston's research and teaching focuses on concentrating solar energy systems and applied non-imaging optics. The concepts developed and the devices invented by Dr. Winston have formed the core of a new technology which carries the promise of making solar energy a truly viable energy source for society. He has had over 200 articles and published in scientific journals and over 60 patents. Thank you for taking this time to give this webinar, and we look forward to hearing what you have to share. Please get started, Dr. Winston.
Well, thank you, Casey. Thank you very much. Casey was an undergraduate student working in my group, and back in 2014, we were just starting a very, what turned out to be a very challenging project with an agency called ARPA-E, which is, they have on their byline, trying to do the impossible. And then as we found out, their projects were very hard to do, and we are still doing the same project, although it keeps evolving, it keeps changing. And when Casey asked me to do this, I mean, what else could I say? But absolutely, since she was a remarkably good student, and something I never told her before was that there was one point in this impossible experiment where all our solar cells were falling off. Okay, and that was very, very unfortunate. We didn't know what to do. It was a weekend, okay, everybody was gone, but Casey stuck around, and she actually ended up gluing back each of the cells that had fallen off, and that rescued us back in 2014, and we're still doing this project. So I have a great debt of gratitude to her. Okay, so let's get started with what I have to tell you. I'm a physicist, okay, and I came to UC-Merced because I felt I'd pretty much done what I wanted to do in physics in my home university, which was the University of Chicago. I'd been a student there, I got my degree there, and I spent almost 30 years there, ending up being the department chair. So that was, I figured that was, enough of that environment. But I think the main thing that really persuaded me was that I was there with my wife, Patricia, and it was February. And February in Chicago, you're buried in snow, right? And here the flowers were blooming, and more importantly than that, the chancellor and someone at that time were very welcoming. So I decided to give it a try, and I'm glad I did. So now I'll start telling you about, not so much about myself, but I'll start telling you about solar energy. So as Casey mentioned, I've always been fascinated by the subject of concentrating sunlight, because sunlight comes down to us on Earth well, it's a pretty good amount if you're especially in the summertime in Merced, but it's actually not very much, about a kilowatt per square meter. And if you think about it, it's actually enough to sustain life on this planet. So it's a very fortunate coincidence, if it's a coincidence, that the solar radiation on Earth is just right for our life to exist. And let's hope we don't goof it up. Okay, so let's hope we don't go into some unfortunate global warming type situation and ruin our home, because right now we have no other home. Anyway, to get on with solar concentration, I like to, being a physicist, I like to think about things sort of, as physicists call it, first principles, or you may think of it as, I want to think about things from the beginning. And I also believe strongly that if you understand something properly, you can explain it to a teenager. So right now I have some grandkids who are almost teenagers, and I feel if I can explain to them, then I've understood it myself. Okay, so a physicist is going to start with concentration, not as a given. I mean, that's engineering, but my engineering friends will hope forgive me for saying that. But as something that you want to understand from the beginning, just what is it and why is it? So I want to connect it to something which we've all known about since the beginning of science, almost the beginning of science, and that was Isaac Newton's understanding how things work. And he certainly is famous for having noticed that a apple from a tree actually falls to the ground. And out of that and his wondering, how come, why did it do that? Came the Newtonian laws of motion. So that's basic, right? So let's start with that. And this little cartoon shows Isaac Newton and the apples falling, and he asked, why does, so I mean, he hypothetically asked, why does the apple fall? And the answer we can give it today, this being 21st century, is because the entropy gradient is downward. Now, don't get scared about the word entropy, but entropy is a very general concept which ties what Newton was thinking about to what makes concentration work, and that's that connection is quite fascinating. I'll describe it a little bit to you. So we'll talk a little bit about entropy. What does that mean? And connect it to apples falling, and also connect it to solar concentration. But what makes this talk, I think, of some interest, hopefully, is that I will talk about projects, and you might think of them as exotic places like Mongolia, like India. Must be a lot of others. I'll mention them. I'll spend some time in Mongolia. So with that introduction, I will continue. Okay, so don't get tuned out by the first few slides, which will tell you a bit about the connection of entropy to concentration. It's a deep connection, and you can have the satisfaction when all this is finished that generally people don't know this. So you'll have learned something hopefully interesting to you, but definitely new to most people. Okay, so to continue, we're going to understand what on earth does entropy and Newton have to do with solar energy concentration. Okay, so the physicist approaches concentration from, as I said, a first principles type way. How and why does it work, and what do you do to make it work well? So the cartoon version of concentration is you have a source of radiation, the sun, and you have some kind of a device, which is shown here as a box, and physicists like to talk about a black box. Okay, so you got black because you don't know what's inside. So if you have a black box or some kind of box into which you can put things, how do you make the radiation from the sun, one, falling on aperture two? How do you make it? How do you concentrate it? And how much can that concentration be on the absorber three? How much? And then how do you do it? Okay. So the again, the division between, roughly speaking, division between physics and engineering would be the physicist is supposed to tell you how well can you do it, and the engineer is supposed to make it work at that level. Okay. So not to anticipate too much, we'll find out that how well you can do it is over 100,000 to 1. In other words, instead of a kilowatt per square meter, it's 100,000 kilowatts, which is 100 megawatts per square meter, and that's the surface of the sun, and that's really hot, right? You may know, if you follow the papers, that there are now probes that are really examining the surface of the sun, very with photographs, and we're not going to land anything on the surface of the sun anytime soon, because the sun is still very hot. It's about 6,000 degrees. But nevertheless, we're studying it with closer, better and better cameras and devices like that, and getting closer and closer, and it's kind of close to me emotionally, because the scientists who first studied this type of phenomena, the sun, carefully, his name is Eugene Parker, and that the satellite's called the Parker satellite. So and he's still alive. That's a big deal. He's still alive, and NASA names a satellite after you. It's pretty neat. He's a very neat person. So okay. So the question I asked was not knowing anybody. The question I asked was, what do you put in that box? Nobody can't look it up. So what do you put in? There's the challenge. Which I often tell the students, what do you do when you can't look it up? Okay, we're so used to looking things up. I mean, everything gets Googled, everything gets looked up. We almost get unused to thinking about things. But this one you can't look up. At least that was the case before we started our work. You couldn't look it up. And by the way, you can look it up now. There's a third edition of our book. Yeah, there's a book of nonimaging optics with I'm going to mention my co-authors, Zhang and Vladimir Oliker. I think that's about it. Both marvelous scientists, and that's coming out. We're trying to get. We're doing the proofreading now. We're trying to push it out. Okay, so okay, enough said about this. Now we'll try to answer the question. I mean, at this point, you're probably anticipating there is a best design. Otherwise, this fellow wouldn't be wasting our time, valuable screen time, talking about this. So there is a best design. So let's see what that might be. Okay, to continue. Okay, here's how you figure it out, and here's where entropy comes in. You figure it out by looking at the what's going on here. So you have a radiation source and the aperture, and if you want to think of the absorber, you can think of it as a solar cell, which makes electricity, or you can think of it as something that heats up and gets really, really hot. I mean, after all, the limit of how hot you can get is close to the surface temperature of the sun. Remember that's 6,000 degrees. And whether you're thinking of Fahrenheit or centigrade, don't worry, they would both be super, super hot. Okay, so we do a thought experiment, since we can't really do this. We do a thought experiment. So we can say that the highest temperature that T3 the absorber can get is the surface temperature of the sun. If you go any higher, you can make what's called a perpetual motion machine. In other words, you could do work without having to pay for it, and that's a bit of the entropy connection, and we sort of know I think both by experience, intuition, and then along comes the science of thermodynamics, which tells us it's so. The absorber will never exceed the temperature of the source. By the way, if it did exceed it, it's easier to set up a perpetual motion machine and solve the energy problem. But the energy problem is formidable, and it's not going to be solved as simply as this. Okay, so if we admit that the absorber, no matter what you put in the box, it might get as high as the temperature of the source. This is all a thought experiment. I mean, it's too high to do. So the argument. You can read the argument. You can. I think the best thing we can do is, since I assume these slides will be kept, so you can go back to them instead of going through them line by line, which is boring. I'd rather just accept that conclusion. It agrees with our intuition. It agrees with our experience. it agrees with what we expect. All right, so no matter what you put in that box, you'll never exceed the temperature of the sun. So let's go on from there. I guess I could comment that I'm told the U.S. Patent Office is continually getting patents how to exceed the temperature of the source. So how to exceed this limit, and then you always, sometimes I get asked, you know, and in the end it's hard to say what's wrong, but there's always something wrong. There's always a catch. There's always something which makes it impossible. In fact, a better way to do that kind of screening, if you were faced with this problem, is ask yourself, well, if this design that's presented to you actually was correct, you could have a higher temperature in the target than at the source, and you know that's impossible. So the second law of thermodynamics will permit that. So that's an easy check, easy test. Although how to make it, how to see it in practice can often be challenging. Okay, so let's accept that. Okay, so it's a way of saying the second law of thermodynamics. So you don't try to go against the second law of thermodynamics, and get in trouble. So the best, no matter what you put in that inside there, the best you can do is the absorber will get to T3, will get to T1. That's the very best you can do. Once you've done that, you can stop. So you know you've done it, and you can stop, and then you can do whatever scientists do with it, or engineers, they do with it. I don't know, depending on what you want to do, you can produce the device or you can write about it. It's a matter of what people do. In my case, I wrote about it because I was a scientist, and boy did I get in trouble. Anytime you get into, after all, this hadn't been done for, how long have people been thinking about this? Well, so the fable is that I think it was, well, one of the Greeks was at the time of Archimedes. It might have been Archimedes. Had thought about this and had tried to make devices. And in fact, Archimedes, I think, is the one who was credited with having soldiers with shiny shields, point them at the sailing boats of an opposing enemy, and they set the sails on fire, which was a spectacular demonstration of the concentration you can do with solar energy, and it was nowhere near the limit, which we'll get to. But it was high enough to burn the sails, which the people who were in charge of the sailboats were not very happy with. So he paid a price for it, unfortunately, and he when the opposing army found him, so the story goes, they killed him. So anyway, that aside, what does that got to do with thermodynamics? It has more to do with people, right? Okay, so let's accept that we don't want to be the same fate as poor Archimedes and lose our lives just because we try to challenge the second law of thermodynamics. Okay, so to continue. So now you have a clue. Whatever you put in that box, you better not go against the second law of thermodynamics, or you get in big trouble. I mean, serious trouble, like poor Archimedes. Okay, so let's let's talk about what we ended up doing. So that's a cross section of one of our designs, which attempts to meet second law of thermodynamics, that limit. And what it looks like is the target is a long tube, because we're going to heat something. Think of it as a water heater, or maybe a heater for something that wants to get very, very hot. Much more than water, or could be making steam, and all kinds of uses. Once you can produce high temperature, lots of things you can do. That's a cross section, and that funny looking whatever makes you think of a bird, wings or something. So that becomes reflective. Okay, so you put a reflective film on that, and you point it at the sun and see what happens. Okay, so what happens is that as the sun gets reflected from that curved mirror, it gets reflected to the tube, which is trying to heat up the liquid inside. Okay, and if you think of where that light is coming from, it's not coming from the whole sky. It's coming from a portion of the sky. In this case, I'm using an angular measure, which is the sine of the angle, and that turns out to be convenient for this kind of argument. And the light can come from a swath of the sky. You can think of it as a ribbon. In other words, it's plus or minus. So 0.5 is 30 degrees. Plus or minus 30 degrees in one direction. The other direction, it's anything, plus or minus 90. But it's plus or minus 30 degrees. And let's just go through this. Let's reverse it. Optics is reversible. So if we send the light back, it should also come from a ribbon in the sky of that kind of angle, plus or minus 30 degrees. So it makes what we call a nice collimator, or you can think of it as a device which sends out a beam of light, which is by itself quite useful. Okay, so you might at this point say, oh, that's kind of boring. But let's see, let's continue. So if you send light rays, what they look like in the case of this funny shaped mirror is we call it collimated. The light's very directional. In this case, it's directional plus or minus 30 degrees. That's where the light goes. It doesn't go anywhere. It doesn't go outside of that. Okay, so here's the however. However, from the time of, did we use Archimedes as an example? From the Greek times, people have always used the geometry of Euclid. Why is that? Because Euclid's even older than these guys, and Euclid set forth the principles what we call plane geometry. So when you go to school, that's the first thing, almost the first thing you're asked to know is plane geometry. Okay, I had a lot of fun teaching my grandson as he was growing up. I think by the time he was 10, maybe 11, I showed him the nice Pythagorean theorem that the sum of the squares of the sides of a right triangle is the square of the diagonal. So the famous Pythagorean theorem already was known to the Greeks, who kind of thought through this geometry, and that's actually not giving credit where credit is due. I'm told, I believe, that the person to first write down these results was not Pythagoras, not the Greeks. This was a this was in Near East, in Egypt, around around 80 something, around the turn of the millennium. So not very far, but not very far from what we still regard ancient the days of the Roman Empire, and also when the Romans moved east, and you got the Eastern Roman Empire. Well, I'm not giving you a course in history, so but I do want to say that partly the reason now we can look at who was doing this. It was a lady who, all we know about her is that she was considered very smart, so smart that she annoyed. This happens to this day. She annoyed people, especially people who resented ladies having this kind of intelligence. So she didn't end up well. I think she was, yeah. History says that she was unfortunately killed. So when I give a class, I have her name in front of me, so I could recite it, but right now I can't. So, but you could just look up the history of the Pythagorean theorem and who actually first wrote it down, and it was this lady. So the sketches of her shows that not only was she was very attractive, and she was very much a leader in her time, and I guess that got her in trouble. So anyway, the theorem holds up. Okay, so if you look at this picture in front of you, if you make that reflector into the proper shape, on the right, it's a nice beam of light. But if you make it into a parabola, boo, the parabolas were what the Greeks invented, right? They invented all the conic sections. So it spreads out like all over the place. Light goes all over the place. And intuitively, you might think, well, if the light goes all over the place, it's probably not the world's greatest concentrator, because it's going to lose a lot of light trying to bring it into a small spot. And sure enough, look at the angular pattern. On the right, it's a nice collimated light. On the left, it's spread all over, and the price you pay is bad concentration. In fact, if you want to know the particulars, the concentration is lower by a factor of pi, which is about 3. And just to jump ahead, when we got into this with our program, which I'll talk about by time, our program manager caught on to this and said, "Oh, that's the pi effect," and he kind of made this into a recognizable term, which I think helped us continue from 2014, and we're still going strong. So that's how things go. Okay, let's continue. So how do you get the right shape? You look it up. You can't look it up. Sorry, you got to figure it out. That's what I'm talking about now. And the figuring out has an interesting connection with what I call Hodel strings. It's a technique that engineers use to figure out how much radiation goes from one source to the other, one wall to the other. If you think you're think of you're in a room, and and how much light, how much radiation is coming from that wall to you, okay? And it turns out that there's a way of, it's a calculation which is pretty boring. But there's a way of shortcutting the calculation by using strings, and I always do this in class. I get I get 2 students to come up to the front, and I give them a bunch of string and some scissors, and and they ask them to stand some distance apart. And ask them, well, suppose one of you is a source of heat, or we're all source of heat. How much of that heat, what fraction of that heat do you think falls from one to the other? And their guess is generally always wrong, because it's remarkable. Even if you stand fairly close, it's remarkable how small that fraction is. Anyway, so the string method was invented by it's credited by an MIT professor, Hoyt Hodel, who's actually quite famous in the solar energy history, and there's a Hodel Prize named after him, fittingly, and he found this formula. So let me continue. It's very neat because you can do it very fast, and it's solid. It saves you from a very tedious calculation. It takes you forever, almost forever. So now, if we work out the implications of this, so in this diagram, just look at the right. AA prime is a source of is hot. It's a strip of material which sends out a lot of heat, some temperature. A3, so A2 is the window through which it falls, and A3 is the end of it, the absorber, A3. And now your job is to make the temperature of A3 as close to A1 as you can. And supposedly, when you work out this, well, let's see how it works out. So the concentration, I'm not going to ask, you can look at these formulas later. They're not our formulas, but nevertheless, I'm not going to do it in real time. So it turns out that the concentration that you can get is less than the one over the probability that no, let me restate. The easiest one is that if you can make the probability from A3 equal to A1, if you make the probability of the heat, we look at the problem in reverse, which is often a good way of solving a problem. And if you can find a way for all the heat from A3 end up at the source, and you get the maximum possible concentration. So okay. By the way, I'm very available by email me or something. But if you look, it doesn't it's just a few lines of it's not very intimidating. Okay, so let's continue. So if you do that, you make that design. You make a design of something which has been called this compound parabolic concentrator, CPC. Now it's called that, even though not a parabola in it. But that's a subject for another talk. Let's see. I basically didn't want people to use my name. I just thought that was not the right thing to do. I prefer to, I just didn't think that was the right thing to do. So it became shortened CPC, and that's what people call it nowadays. And okay. So that's the string construction, and that's how you make these things. And in the next few minutes, I'll try to give you some examples of what they look like. So this is what it looks like, but this is now a drawing, not real. It's a drawing. Okay. So those are the tubes. They happen to be vacuum tubes, and those are the mirrors, and the whole thing is pretty. I think it's very pretty. We use it for a cooling project. How do you use heat to make cooling? You can do that with thermodynamics. So if you have a source of heat, you can cool your room, and that's very convenient, especially this time of year in California, my part of California. Okay, and this shows how well it worked. By the way, so this just shows that. So this is the efficiency, and flat is good, right, over all angles. So from plus minus 30 degrees, 60 degrees, it's very uniform. And those are real experimental points. Okay, and then if you know how well you cool, the blue is the cooling curve. So the I have just a warning to finish up, but I'm going to continue for a while. So the blue is the cooling you produce. The red is the heat. They're about 1-to-1, not bad. And that's how you cool off your space. Now you might say, oh yeah, but the sun's got to be shining. Nope. The raggedy one is what happens when you have clouds, so the sun is kind of not shining too well. But your angular acceptance, plus or minus 30 degrees, is so huge, you tend to get enough light going through to keep you cool anyway. So you can see that when the heat gets very raggedy, the cooling is pretty steady. So that's good. Okay. Okay. So after this came out, this was 2014. After this came out, lots of people took it on, and I think the rest of this talk, to the extent I have any time, is to go to where it was done. Let's see. What I need to get this in. Okay, let's see if I can get this to work. Click, 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 click. Control click. Okay.
Roland, we can't hear the video.
Why not?
It might, is it muted?
What? I
Is
can
it
hear it.
muted?
What's going on?
I cannot hear it on the
What?
webinar.
Well, you know, the pictures will do it, Casey.
Okay.
The pictures will do it. That's what a collectors look like. Now this is hard to hear, so you're not missing much. It's just showing you how you can use heat to purify water. So purifying water is a big deal, especially in our part of California. So if you can have a water purifier, and this one works on heat, you've done a good thing for the environment. Can't hear it, huh? Oh well. Okay. Well, let me go on to something else then. Okay, you got the idea. Let's see. So the next thing to do is to go through. Where am I other? I've done this. Now I need to do some examples. Okay, let's see if we can get this done. Okay, so we like to take on challenging projects. Can you hear me? Casey?
Yes.
Okay.
Yeah.
So one challenging project that came our way was using solar in Mongolia. Now, the reason that caught my eye was that if you can do, Mongolia is the coldest, pretty much the coldest place on Earth in terms of, I mean, the capital of Mongolia Ulaanbaatar is the coldest capital in the world. So I figured if you can make it work, if you can make solar energy work in the coldest place on Earth, that's a good test. So let's go through this before it's too late. How do you get through? I need the presentation mode. Darn it. How do you do presentation mode?
Yeah, remember that lower little symbol of the little, what, 2 over, 2 to your right, 2 to your right.
This way?
No, right. The last one on the right.
Okay, good. Okay, so Mongolia. So Mongolia, we don't think about much, but it was once the largest empire the world had ever seen. That's Genghis Khan. So the empire that Genghis Khan put together, it included China and included part of Europe. So a lot of the known world was included. Okay, so it's really cold. We planned that this is a cafe in Berkeley where we made that plan to do that. Okay, so here's the university, Mongolian National University. I've also put everything is in Russian. Mongolia was ruled by the Soviet Union until not too many years ago. So everything is still in Russian, which was easy for me since that's a easy language for me. Okay, so that's the university students. Here I'm with my friends, my wife, Patricia, and the people, me, and the people who financed this trip and so on. Okay, and that's Genghis Khan. We're saying hello to Genghis Khan. Yeah, it's too hard to see. I want to give you an idea of how smoky the place is. It's incredible. Okay, it's incredibly smoky. It's because it's the heat is done by burning things, and you can hardly see the sun. So that's the upper left is a traditional house. Upper right is inside the house, and the lower right is myself and my wife. Okay, so our solar arrays look like this on the right, and the one on the left is what they look like. I think this one is in it's either in India or some exotic place. We have people doing this in all over the world, and I think this was in India, if I'm not mistaken. But the one on the right is at UC-Merced. You can still see it. Okay, that's just how it all works. You've seen this again. Okay, so that's Bennett was in the YouTube video, and here he is next to one of our collectors. And here he is in Mongolia, so you can see very cold indeed. Mongolia, tough place to do solar energy. It's actually a very beautiful country. So when Bennett landed and got himself to the university, he set this thing up, the collector up, pretty quickly on the rooftop. And then he measured the temperature, and the temperature outside was, I think it was minus 14 degrees centigrade. And then the temperature inside the collector was 310. So that really amazed people who were there. And that's just pieces of their work there, which I don't have time. So they had a big party. That was very important. So here the big party is the Mongolian flag and the US flag and the UC Solar flag, which is our organization. And so happy story, happy ending. And I think my time, I still have a few minutes. That's just more. They tried some work on thermal storage. And okay, so this is somewhere else in the world. This is in Dubai, of all places. So we have an engineer in Dubai who's doing this. And the reason for showing this is that it can be done anywhere. And then the reason for showing this is that I could never do this at this at our university. I think at any university, no university is going to let you have that kind of equipment around. Although right now we're using pretty big equipment to set things up. So anyway, and we certainly couldn't do this with students, even they would not pass the safety code. So anyway, let's see more of that. And that's Bennett. So Bennett had some off time, and he got a camel ride. We're all very jealous. He got a camel ride, and he thoroughly enjoyed Mongolia. Casey, I said time for questions, or what should I do now? Oh, wait a minute, I gotta show a picture. So this was Casey in the early part of that project, and a number of the other students, most of whom by now have graduated. So, and that monster thing at the beginning was our first stab at doing the ARPA project, where we have to produce both high temperature and large scale, and we're still there today. Today we're in Plaster City, well, setting up in Plaster City, California, which is pretty much on the border between Mexico and California. And we hope that works out. We'll see. Okay, I think that's what I'm going to show.
Yeah,
If there's time for questions, I'll take them.
Yeah, of course. Yeah, thank you, Roland, so much for giving this presentation. It was very helpful. We have Robbie who asked, since many solar systems are reaching the end of their life, do you think that these panels will end up in landfills or will they be recycled?
Well, let's see. Remember, these are mostly heat, so we don't have things that are big disposal problem. Mostly metal. I mean, depending on the part of the road you're in, the metal will be recycled. The reflecting film is really thin, so there's just not much there. I mean, it's mostly structure, and structure you wouldn't throw it away. It's too valuable, so you use it for some other purpose. I think in that sense it's recyclable. But there's no, if you're getting at hazardous waste, I don't think there is any hazardous waste.
Right. Okay. And is there any toxic waste produced with solar panels when they are thrown out?
Is there any way to produce it? Well, wait a minute. What happened to? Okay, so you showed that little video of Bennett. So we hope it'll get produced in large quantity. I think right now the production is something like a megawatt a year, something like that, which is not nothing. It's a fair amount of energy, but it's not huge. It's still way behind solar cells. Solar cells have had a remarkably good growth curve, and we're catching up, trying to catch up.
Okay, great. Well, we don't have any other questions in here. Do you have any last comments for the audience, Roland?
What comment?
Do you have any last comments?
Any comments? Any last comments? Well, I mean, come visit us once we're done. I mean, right now we're kind of shut down with a quarantine, but some of our students are working even today, and then we welcome visitors. Then there's lots of stuff that you can read. Let's see what I was going to say. Book is coming out later this year, I hope. What else? And I'm always open for an email question, and did my email address end up somewhere? I think. Casey, you've got it, right? Just
Yeah.
if you have a question that you'll think of between now and later, just send me an email and I'll try to answer it. Yeah, I guess one more remark is for the students, get involved in something that really excites you. Don't do something just because it offers you a job. I mean, the job is important, but beyond that, make sure you're doing something which helps people, which you can be proud of. So that's kind of my advice. And the students who have graduated have done very well. Casey is one example, and there are some others who have done very, very well as they left the university, and they're on their way to being very very successful in what they do, which is a great pleasure for me. So so right now, energy is a good field to get into because it's needed and it's good for people. And make sure that both you cross off both of those. You want to be good for people, and not something that's bad for people. Okay, so. And don't worry about the money should not be a prime consideration. If you're doing what's good for people and it's what's important for people and you're doing it well, the money will take care of you. You don't need to worry about that. So that's my advice. People, starting out. Is this a good profession? I think it's a very good profession.
Great. Thank you so much, Roland. We appreciate you doing this webinar today, working with the American Solar Energy Society and our board member, Casey Chang. Thank you for the contact and the ASES technical divisions for helping put this together this month. But thank you so much, Roland. We hope to have you on again in the future.
I missed what you just said, but I take it we're wrapping up, right?
Yes.
Okay. Anything I need to do?
No, yeah, just wanted to thank you for doing the webinar for us today, and we hope to have you on again in the future.
Thank you much, and come visit. Come visit us, Casey.
All right, sounds good.
Okay.
Thanks, everyone.
Thank you.